feedback to the operational amplifier. Now we'll see one circuit in open loop condition, and after that we'll start the operational amplifier with positive feedback. Now this is the circuit. We have this inverting and non-inverting inputs. Now in this circuit we have kept this non-inverting input at ground terminal, and we have applied a sinusoidal voltage to the inverting input of op amp. This circuit is called zero crossing detector, and in this zero crossing detector the operation will be based on the fact that open loop gain is equal to infinite, but practically we know that this open loop gain equal to infinite is not possible. Now we'll start the analysis of the circuit. Parallelly we will draw the graph of the circuit. This is input voltage, and here we will draw the output voltage V0. Input is sinusoidal voltage and output is we will see how the output will vary with the input voltage. Now in this case this voltage is V1, this voltage is V2. Now we'll start the analysis. We know that the output of operational amplifier is AOL into V2 minus V1. If V2 is greater than V1, then output will be V0 will be equal to plus Vsat. If V1 is greater than V2, then output V0 will be equal to minus Vsat. Now we'll start the analysis. Now we start from this point, from 0. If we increase with this sinusoidal voltage, at this point we have Vi equal to V1 is positive. If V1 is positive and V2 is 0, then it is clear that V1 is greater than V2, and if V1 is greater than V2, output will always be negative and it will go to negative saturation. So from the starting V1 will be greater than V2 and output will be minus Vsat. Now if we increase this V1, again V2, this voltage 0 voltage is V2, this V2 is less than V1, and again output will be minus Vsat. If we are at this point also V1 is greater than V2, again output will be minus Vsat. At this point both are equal, both are 0, but exactly after that point V1 is going negative. If V1 is negative and V2 is 0, obviously V2 will be greater than V1. So at this point, when both are 0, after this point the output will be switching from minus Vsat to plus Vsat, because after this point the V1 voltage becomes less than V2 voltage. If V2 is greater than V1, then output is positive, and this positive voltage will be plus Vsat. Again uh, uh, at this point we got v1 v2 greater than v1, and in this part of graph v1 is negative and v2 is 0. So for this part of graph always v2 will be greater than v1, so output will be plus vsat. And now at this point again v1 will become greater than v2, so output will again switch from plus vsat to minus vsat. And at this point again output will switch from minus vsat to plus vsat. In this way we'll get a graph. So in this circuit we have seen the output waveforms. In these waveforms we can see that whenever this input sinusoidal voltage whenever this input sinusoidal voltage crosses zero reference line, output changes its states. Means if it crosses this zero line, here we can see that output was changed from minus vsat to plus vsat. And at this point input sinusoidal voltage again crosses zero line, so output again changes from plus vsat to minus vsat. So at every point where input signal crosses the reference line zero line, then output changes its state either from plus vsat to minus vsat or from minus vsat to plus vsat. So this circuit is therefore called as zero crossing detector. Now we'll see the comparators with positive feedback. This circuit is also called as schmitt trigger circuit and sometimes called as regenerative comparator. Zero crossing detector is also a comparator. In zero crossing detector we used op-amp in open loop condition, but in schmitt trigger circuit we will be using this op-amp circuit with regenerative feedback, means positive feedback, so it is called as regenerative comparator. Now in this circuit we have applied this positive feedback, and with this positive feedback we will be increasing the gain of this operational amplifier, and it, it will have the characteristics like ideal operational amplifier. We'll apply a voltage Vi at the input of this comparator. Now at this point output voltage is at this point the voltage is V0, and at this point the voltage will be the voltage of non-inverting terminal, that is V2. Here we will give another name to this voltage and to this voltage. At this point the voltage will be called as VB, and at this point the voltage will be VA. Again this thing will be true that if VA is greater than VB, will V0 will be negative. and if VB is greater than VA, then output will be positive. Based on these two assumptions, we'll start our analysis. At this point, the voltage is VB, and this voltage VB can be calculated as VB equal to, by potential division rule, this point voltage is VB. By using potential division rule, we get V naught into R1 upon R1 plus R2. This is VB. And we know that in this equation, VB depends on V naught. V naught can have two different values. If V naught equal to plus Vsat, if V naught equal to plus Vsat, then we have VB equal to VUTH, upper threshold voltage, equal to plus Vsat into R1 upon R1 plus R2. This is called upper threshold voltage. Now if V naught equal to minus Vsat, then VB equal to VLTH, that is lower threshold voltage, will be equal to minus Vsat into R1 upon R1 plus R2. It will be lower threshold voltage. Now we'll draw the output waveform for this operational amplifier. We have got the expression for VUTH and VLTH already. We will apply a sinusoidal voltage at the input terminal, that is Vi will be a sinusoidal voltage. This will be the input voltage Vi, and here we will plot voltage VB. VB can have two values, VUTH and VLTH. Now we, in the waveforms, we will be comparing VA and VB continuously, and based on the comparison, the output will be either plus Vsat or minus Vsat. Now this Vi voltage equal to Va, and we will compare this input voltage with values of Vb. This voltage is VUTH, this voltage will be VLTH. Now we'll start the analysis. Before starting, remember one thing, that VB have two values, VUTH and VLTH, but both the values cannot be there at the same time. There will be there will be different value for different output. If output equal to plus Vsat, then then VB will be VUTH, and if output equal to minus Vsat, then VB will be VLTH. Now initially, here we will plot the output waveforms. Output voltage will be plotted here. Plus Vsat, minus Vsat. Now all the values, all the graphs are plotted against time. Initially we will assume that v naught equal to plus vset. It can be assumed as minus vset also. There will be a difference in the starting of the waveform, but the information from the waveform will be same in the both the cases. If v naught equal to plus vset, then at t equal to 0, uh, when v naught equal to plus vset, vb will be equal to v uth, that is plus vset into r1 upon r1 plus r2. This will be the value of vb, which means when output v naught equal to plus vset, vb equal to v uth. If vb equal to v uth, this will be the value of vb. And remember that vb cannot have two different value at the same time. It will have only vuth value when output equal to plus vset. So initially we have assumed that output equal to plus vset, and at this vset value plus vset value vb equal to vuth. If vb equal to vuth, we will have this value as valid value of vb. Now we will compare the input voltage with this vb value, that is vuth. Assume that there is no vlth here in this graph, there is only vuth. Now if we have vi at this point, we can compare these two voltages. If vi is here, then vuth is clearly seen to be greater than this vi voltage, and for this point the output is plus vset, means our assumption is correct. Remember one thing, if you assume v not equal to minus vset, then also you will get the assumption to be correct. Now if we increase this vi voltage, at this point also vuth is greater than vi, and output is again v plus vset, and if output is plus vset, vb equal to vuth. At this point, when this point is crossed, vi will be greater than vuth, so va will become greater than vb at this point. And at this point when va becomes greater than vb, va means vi, va greater than becomes greater than vb, output switches from plus vset to minus vset. If output changes from plus vset to minus vset, we know that vb becomes vlth, that is minus vset into r1 upon r1 plus r2. So output when switches from plus vset to minus vset, vb becomes vlth. So vb also changes from vuth to vlth. Now forget this dotted line, that is vuth, because vb is no longer equal to vuth, it is now equal to vlth. If it is equal to vlth, we'll compare this point to this point. va is greater than vb, clearly seen, so output will be minus vset. If we are at this point, if it cross this point, we know that this at this point, at this time, vb is not equal to vuth, means there is no reference line at this point, so there will be no effect on the output. Now when it cross 0, again there will be no effect. When it cross this point, which is the present value of vlth, when it cross this point here, va becomes less than vb, and when va becomes less than vb, output switches from minus vset to plus vset. If output changes from minus vset to plus vset, vb will be again plus plus vset into r1 plus r2, means it will become again vuth. And again, when we increase this graph at this point, again va becomes greater than vb, and output again switches from plus vset to minus vset. At this point again vb greater than va, so at this point output again switches from minus vset to plus vset, and vb switches from vlts to vuth. In this way we get a square wave at the output. In this Schmitt trigger circuit, we have applied a sinusoidal input, and at the output we have got a square wave. So a Schmitt trigger is basically a square wave converter which converts input periodic waveform to a square wave. One more thing we'll have here, that from this point to this point, or from this point to this point, input signal completes one cycle, and from this point to this point again input signal completes one cycle, and the time required for one cycle is time period, that is t. If we project these 2 points at the output waveform, we got here that the time period of input waveform is equal to time period of output waveform also, because in this particular time t, output is completing its one cycle. So output periodic waveform will have a time period which is equal to the time period of the input waveform. So a Schmitt trigger circuit is a square wave converter. Also, output frequency is equal to input frequency. Hysteresis curve for Schmitt trigger circuit. Hysteresis curve is also called as transfer curve of the Schmitt trigger circuit, and this hysteresis curve is a graph plotted between output voltage V0 and input voltage Vi. Remember that this Vi voltage is a sinusoidal voltage which was applied at the inverting input of op amp, and output can have two different values, that is output can either be plus Vsat or minus Vsat, and we'll be comparing this input voltage with Vb, because this is the voltage at non-inverting input, that is Va. Vb have two different values, VLTH, VUTH. Now we'll start the comparison, and we'll draw the waveform for output, graph for output. Now remember one thing, that a hysteresis curve is drawn by varying the input voltage from minus infinity to plus infinity, and the second part is drawn by varying Vi from plus infinity to minus infinity. Now we'll start. First I take Vi equal to minus infinity. From minus infinity, if you see, VLTH and VLTH both are to the right hand side, and if both are to the right hand side, both will be greater than minus infinity. If both are greater than minus infinity, we don't know what is the value of VB, but whatever may be the value of VB, that is VUTH or VLTH, both are greater than minus infinity. So in this case, VB is greater than VA and output is plus VSAT. Now if output is plus VSAT, it is confirmed that VB is VUTH. If VB is VUTH, then we will compare now the values of VI with VUTH. If we increase this VI from minus infinity, this point will be compared with this VUTH. Of course, VUTH is greater than this point, this voltage, so output will again be plus VSAT. At this point, the comparison again VUTH is greater than this point voltage, this voltage, so output will be plus VSAT. Now, when we cross this point by moving this point, there will be no effect on the output because VLTH is not the valid value of VB at this time, because at this time VB is VUTH. Now if we increase beyond VLTH, again comparison will give output equal to plus VSAT. At this point also output will be plus VSAT. At this point also output will be plus VSAT. At this point output will be plus VSAT. And when we cross this point, at this point VA is going beyond VUTH, means VA will be greater than VUTH, that is VB, and output will be minus VSAT. So when we cross this point, at this point VA is greater than VB, so output will be minus VSAT. Now if output is minus VSAT, VB value will be changed to VLTH. Now if we further increased VA, this point will be compared with VLTH, not VUTH, because before this point the output was minus VSAT, and for minus VSAT output the value of VB becomes VLTH. Now for all the points beyond this, the comparison give VA greater than VB and output will be minus VSAT. So if we join all these points, we get a graph like this. This is the half part of a hysteresis curve. Now the next half will be drawn by varying VA from plus infinity to minus infinity. Now if we select VA equal to plus infinity, this plus infinity will be greater than VLTH and VUTH both. So whatever may be the value of VB, that is VLTH or VUTH, VA, that is infinity, is greater than both the values, so output in this case will be minus VSAT, because VA is greater than VB. Now we will decrease this value, but before that, as V0 is confirmed to be minus VSAT, so VB will be VLTH. Now if we decrease this value, comparison with VLTH, VA will be greater than VLTH, so output will be minus VSAT. When we cross this point VUTH, there will be no effect on the output, because at this time VB is not equal to VUTH. So again, when we reach at this point VLTH, VA will be compared, and again VA is greater than VB, so output will be minus VSAT. In this way we'll get output minus VSAT. At this point it is VLTH. When we cross this point, VA becomes less than VB, VLTH. So at this point the output switches to plus VSAT. Now as output becomes plus VSAT, VB becomes VUTH. So all the points on this line will be compared with VUTH, and as VUTH is greater than these points, the output will be plus VSAT. So we get a graph like this. We get a graph like this. So This is the hysteresis curve, complete hysteresis curve for a Schmitt trigger circuit. In this hysteresis curve, we can see there is a rectangle, and this rectangle has its top edge at plus Vsat, bottom edge at minus Vsat, side edges are at VUTH and VLTH. So it is not necessary to know the procedure to draw the this hysteresis curve. If we know these four values, hysteresis curve can be drawn directly. Now we'll solve some examples on Schmitt trigger circuit. Get examples. Calculate VUTH, that is upper threshold voltage, VLTH lower threshold voltage, and VH, which is called hysteresis voltage. For a Schmitt trigger circuit, shown in the figure. Now this is the circuit given in the problem. Now we'll start the analysis. In this circuit, uh, take this as 2 kilo ohms, and we have these voltages as plus 15 volt, minus 15 volts. These values will be equal to plus Vsat and minus Vsat. Now for this Schmitt trigger circuit, we can calculate Vb by directly applying this voltage division rule. Vb comes out to be V0 into R1 upon R1 plus R2. Now substituting R1 and R2, we get 2 by 2 plus 4 into V0, which is equal to V0 by 3. Now the value of Vb will become VUTH if V0 equal to plus Vsat. Plus Vsat is given plus 15 volts, so V0 will be equal to plus 15 divided by 3 will be equal to plus 5 volt. VLTH will be equal to minus 15 divided by 3 equal to minus 5 volts. Now we have got these two voltages, and one more hysteresis voltage is to be calculated, but before this we will draw the hysteresis curve for this. We know that for hysteresis curve, upper and top and bottom edges are at plus Vsat and minus Vsat, that is plus 15 and minus 15 volt. VUTH, VLTH, at this point there will be side edges. VUTH is plus 5 volt, VLTH is minus 5 volt. Now we'll draw the rectangle of the hysteresis curve. This is the complete hysteresis curve. Now this difference in the side edges is called the hysteresis voltage, and it can be calculated as VH equal to VUTH minus VLTH, which is equal to plus 5 minus of minus 5 equal to 10 volts. So hysteresis voltage is 10 volts. Now the next example, calculate VUTH, VLTH and VH hysteresis voltage. Everything is same in this circuit. All the things are same in this circuit. There will be a small difference that will remove this ground and apply a 2-volt source here. This voltage is called reference voltage. Now when this reference voltage is applied, the VB value will be different in this case. Now this is the network from which we are calculating the voltage VB. Now for this network we will calculate the VB value. Up to now we had only single source at the top of this voltage division network, but there are two voltages here, and for this network we can calculate the VB value as VB equal to, first V naught will be considered, so V naught into 2k divided by 2k plus 4k as in the earlier case. But there will be an additional voltage at VB due to this 2-volt source. It will be 2 volt into 4k divided by 2k plus 4k. So it will be V naught by 3 plus 4 by 3. This will be the VB voltage. Now VUTH is the voltage when V naught equal to plus 15 or plus V set. So VUTH will be plus 15 by 3 plus 4 by 3. It will be equal to 19 by 3. VLTH will be equal to minus 15 because V naught will be minus V set by 3 plus 4 by 3 will be equal to minus 11 by 3 volts. So VUTH VLTH will be here, and VH hysteresis voltage will be equal to VUTH minus VLTH will be equal to 19 by 3 minus of minus 11 by 3 will be equal to 10 volts. Now if we draw the hysteresis curve, hysteresis curve will be like this. This will be minus 11 by 3, this will be plus 19 by 3, this will be plus 15 volt, this will be minus 15 volt, and this difference is 10 volts. Remember that in the earlier example also we had this difference equal to 10 volts, means everything is same in the hysteresis curve. Everything is same in the hysteresis curve. The only difference is that the hysteresis curve is shifted to the right because we have applied a positive reference voltage. If reference voltage is removed, the hysteresis curve will be like the previous case. So with a positive reference voltage, hysteresis curve shifts to the right, and if reference voltage is negative, hysteresis curve shifts towards left hand side. Now take one more example. Consider schmitt trigger circuit shown below. This is the Schmitt trigger circuit shown in the figure. Now a triangular wave which goes from minus 12 volt to plus 12 volt is applied to the inverting input of the op-amp. Full stop. Assume that the output swings from plus 15 volt to minus 15 volt. The voltage at the non-inverting input switches between options are given: A plus 12 volt to minus 12 volt, option B minus 7.5 volt to plus 7.5 volt, C minus 5 volt to plus 5 volt, and D 0 to 5 volt. Now for this hysteresis curve, input waveforms are given that it is a triangular wave which goes from plus 12 volt to minus 12 volt. But in the previous analysis of Schmitt trigger circuit, whenever we want to calculate the values of VB, that is VUTH and VLTH, the voltage at non-inverting input means VUTH, VLTH are to be calculated. And remember that in the previous analysis we never included any input voltage in the calculation of this inverting non-inverting input voltage, that is VB, that is VUTH and VLTH. So in this case also input voltage, input waveform doesn't matter. The VB can be calculated using this network which is connected to the non-inverting input of op-amp. Here the non-inverting input of op-amp is there, and at this point both the points are same. At this point the voltage VB will be calculated. At this point the voltage is 15 volt, and here the voltage is minus 15 volt, and here the voltage is V0. Now this VB voltage will be calculated by applying KCL to this network at this point. Now we'll do the calculations. Now if we apply KCL at this point, applying KCL at VB, if you apply KCL at VB, there are three currents, I1, I2 and I3. Both are outgoing, so I1 plus I2 plus I3 should be equal to incoming. There is no incoming current, so it will be equal to 0. Now for this current I1, we'll write the expression. It will be VB minus of minus 15 divided by this resistance. These three resistances are of 10 kilo ohms. I forgot to write in the example in the problem. These three resistances are of 10 kilo ohms. Now divide by 10 kilo ohm plus I2, this current will be VB minus 15 divided by 10k, plus I3 will be VB minus V0 divided by 10k will be equal to 0. Now the denominator of all the three terms is same, so it will be taken in common and will be shifted to 0. So expression now will become VB plus 15 plus VB minus 15 plus VB minus V0 equal to 0. This plus 15 minus 15 will be cancelled, so 3VB equal to V0. So VB equal to V0 by 3. If V0 changes from plus 15 to minus 15, VB changes from plus 542